back. Today we're going to be looking at our new unit, waves. First of all, we're going to be talking about waves in one dimension, and there's a lot to this unit, and so we're going to be at it for a little while. You can follow along in your notes, and if you ever need to pause, go ahead and pause and write down the information that you need to. A wave is basically a disturbance that transfers energy. And the key point here is that it's not actually transferring the matter. And we're going to be looking at some examples as to what that actually looks like and why it's actually transferring energy and not matter from one place into another. Now, there's two main different types of waves that we look at. The first wave is the mechanical wave, and it needs an actual medium to work through. Basically, if it's kind of traveling along from point A to point B, it's going to need a particular medium to work within. So whether that be some type of solid, some type of liquid or gas, it will need something in order to travel from point A to point B. And a medium is any material through which the energy is transferred. So a couple examples could be something like sound, and sound could be traveling through water, it could travel through air, and the water and the air would be two different types of mediums. You could even look at water waves when you're at the ocean, when you're at West Edmonton Mall, and the wave machines and how the waves travel from, again, point A to point B. And so there, the water is the medium. The second type of wave you're going to be looking at would be the electromagnetic wave. This type of wave does not require a medium. So you could have it travel within a vacuum when there is no other matter in there, there's no medium. It's going to be able to still propagate. It's going to be able to still go from point A to point B in those situations. And a couple examples would be the radio wave or even the microwave. There's something that's a little bit interesting too. The microwave is actually mostly for point-to-point communications systems, that is, to convey all types of information. And there was some random historical fact that I kind of learned about where in the early radar detection, it was built, I'll start again, in Hawaii, atop the Kahuku point in Oahu's northernmost tip, there was a station that actually detected the first wave of Japanese aircraft on their way to attack Pearl Harbor when the planes were still 132 miles out, or just over 200 kilometers away. However, because the system had just been in operation for about 2 weeks, it was considered unreliable and the warning was ignored. Over the course of the war, radar was improved and refined, and it has since become an essential element of national defense and civilian air traffic control. Microwaves as well can be used to transmit thermal energy and thus used in microwaves. And for anyone that likes to cook in their microwave anyways, right? Here would be the classic example of the wave. As you can see, it seems like the people are similar to or akin to the medium. While in this case here, you have particular materials, the humans, and all they're doing is going up and down, but they're just doing it in a timed manner. So that the people aren't leaving their seats; they're just kind of going up and down, and that's all they're really traveling is up and down. They're not actually moving along. So it still appears that the wave is happening, but it's not as if the people are traveling from point A to point B. So if we're talking about the matter isn't really moving along with the wave, so to speak, right? It's actually moving perpendicular to the wave. So as the wave moves from now the right to the left, all the people are doing is standing up and then sitting back down. So they're perpendicular to the wave. All right, move on. So there's two different types that we can be looking at here wave-wise. We're going to be starting with the transverse, and even within that, you can have a pulse, or you can have something that's oscillating or continuous. And so the transverse pulse, this is an example of just a transverse wave. The direction of the particles, I already mentioned this before, is perpendicular to the direction of the pulse. So if, for example, this pulse was moving to the right over here, what's happening is these particles are moving upwards and then they're moving back down, but they're only staying in this one position right over here. And this particle right over here, again, is only moving upwards and then downwards. And so let's take a look at this example in just one moment here. So we have the medium particle motion, and then we have the actual direction of that the pulse travels in. And so if we go to this link right over here, let's take a look at, first of all, just one pulse. And there's going to be a variety of different examples that we could be looking at. So this first example here has a fixed end, and it actually reacts differently in different settings here. So if you look at the top, you have a fixed end. And so when you send a pulse, notice what ends up happening. And you can even determine how much dampening there is, or if there's no dampening at all. In reality, there's always going to be some dampening because there's going to be some energy that's going to be lost along in the system. If we turn to this to none, make a guess as to what you think is going to happen here. So it appears that with the same kind of amplitude that it has when it first starts, the wave is what it actually has when it reflects off of this fixed end over here. Let's restart this. Now, if you increase the dampening a little bit, look what ends up happening here. You see that the amplitude of this wave decreases as it goes along there. Each of these affects what happens to the wave, whether you have more or less tension. So imagine that you were actually holding a slinky when doing something like this, and I wish that we would actually be at school, because then we could actually give this a try, play with some of the slinkies and then give it a try and see what actually happens if you pull it a little bit tighter or if you hold it a little bit looser. Look what ends up happening now. So let's go back to the no dampening, have it a little bit looser, and see what ends up happening now. It might not look that much different. So let's see if we decrease it all the way, how that actually changes things. And let's just restart this. So you can see that it definitely changes the way that the wave reacts. That's not a good representation, so just restart that, and there you go. So this would be for a fixed end over here. These are all going to be examples of transverse waves right here. And if we send just one pulse, that's all it's doing, right? It's just one pulse, and then now it's just kind of reflecting, and it keeps going. Why? Because of this dampening is set to none. Once we increase that a little bit, after a while, it goes back to kind of an equilibrium state. You could set one more pulse there, and as you can see, as time goes along, it decreases. Let's look at another example here where you have, say, a loose end, and look how that actually reacts. And I'm curious to see if you notice the difference between that and the fixed end. So let's decrease that a little bit. How is that one different than this one right over here? So make sure that you take note of the difference between what's happening when it hits the fixed point or when there's just a loose end. And if there's no end, look what ends up happening now. It just goes on for infinity right over there. So let's take a look at what each of the parts of the wave are, what they're called, and get a little bit deeper into that. All right, with periodic transverse waves, they're going to be produced by a disturbance that is oscillating, aka continuously moving. And so I guess I'm going to have to go back to that applet in just a moment to show you what that looks like. It could be a skipping rope, a hand oscillating a rope or a spring. Another example would be a light wave, and then even sound waves from a speaker. And so before we just get into the parts of the wave, let's just quickly show what an oscillating wave looks like. And so this is continuous motion right here. Let's put that on pause and bring it back to our first example with a fixed end. Let's put it into slow motion just so we get a good picture as to what's happening here. So as you can see, if you're just taking a look at just one of the particles of matter within this spring, for example, all it's doing is going up and down, but it still appears that the wave is traveling. Here, it's just kind of going oscillating up and down, and we'll be talking a little bit more about some of these other pieces of the wave in just a bit. All right, let's take a look at a loose end now. I'll send you this link so that you can always play around with this a bit too. It's nice to be able to play with some of these, even changing the frequency and seeing how that affects things. So if we went back to normal speed there, and how the frequency affects the wave, and even the amplitude does as well. And so each of these things can affect the wave a great deal. And so it's nice to kind of just play around with it to see what happens, how things change as you go about doing that. So this here, again, is the periodic transverse wave. So again, it's continuously moving. So the parts of the wave, we have the equilibrium position, kind of like at point zero, and you're very familiar with this when you're drawing graphs. There is the top of the wave, which is called the crest, and then the bottom is called the trough. When measuring the amplitude, you always want to make sure to be measuring it from the equilibrium position to the highest most point, the crest, or from the equilibrium position to the lowest point of the trough. And so just be aware of that the amplitude is only this distance right over here. It's not from crest all the way to crest. So it's not from this point all the way to from crest all the way to trough. It's always just from either crest to the equilibrium or from the equilibrium to the trough. If we're looking at what one wavelength is, and this is a Greek letter right here, lambda, and it's the distance from crest to crest, so the midpoint over here to here, or it could be from trough to trough. Again, if you needed to pause, just quickly pause, and then we'll just keep it going from there. So some definitions here. We have a cycle. What is a cycle? It's one complete up and down movement and back. And so sometimes we're going to be having to say, well, okay, how long does it take to complete one cycle? Or maybe you're going to be measuring a sound wave and there's 426 cycles per second. A wavelength is normally measured in meters, and it's represented with the Greek letter lambda. And in this example here, the horizontal length of one cycle of a wave, so aka the distance between two successive crests or troughs. It's a distance from a crest to the next trough is only half of the wavelength. So like I said, don't measure from crest to trough. You're going to be measuring either from crest to crest or trough to trough. The frequency, represented by the letter F, is the number of cycles per second. So how many cycles actually occur every second? And some of you may be familiar with Hertz and measuring sound frequencies, and that if you were, say, to hear a kick when listening to a song, those frequencies usually range between 20 to 30 Hertz all the way to a couple hundred, but like the main frequencies of kick sound would be right around 100 Hertz. If you're talking about a singing voice, you're looking around about 1,000 to 4,000 to 5,000 Hertz. And so the human ear normally 40, 50 hertz all the way to about 15, 20,000, somewhere around there. And that's dealing with hertz. What is a hertz? It is 1 over seconds. So when you see 1 over s right over here, that's a hertz. It's 1 over seconds. And you can even determine that based in this example right over here. If you say the number of cycles per second, when you go cycles divided by seconds, you end up with a unit of 1 over seconds, which is called a hertz. The next one is the period, and it's represented by a capital T, and it's the length of time for one cycle to complete. So it's kind of the inverse of the frequency. So it's the length of time for one cycle. So how long does it take for one cycle to complete? So to get from one trough to the next trough, or one crest to the next crest. This one is measured in seconds, and that should also make sense because the inverse of 1 over a second is a second. So here we have these formulas that are given. So either a period is equal to 1 over the frequency, and a frequency is just equal to 1 over the period. Next, we have the amplitude, represented by capital A. It's the maximum height of either a crest or depth of a trough measured from the wave's equilibrium point. The distance from the top of the crest to the bottom of the trough is actually twice the amplitude. Be aware of that. If we're looking at wave velocity, aka how fast a wave moves, it's the speed of the wave, not the particles in the medium. So it's the speed of the wave, not the particles. Because remember, the particles are often just moving perpendicular to the direction of the wave. So just like people, when they're doing the wave, all they're doing is going up, sitting back down, but it appears that the wave is moving. How fast is that wave moving? That's the speed that we're looking for. So if we're looking at an example now, you're walking down the beach, missing the good old days of quarantine, thinking about physics. You count 23 waves run over your feet over a time period of 52 seconds. Now, if you're asked to say, hey, well, what's the frequency? What's the period? What you should be asking for the period is, well, how long each wave takes. How long does it take for each wave to go? And so in this example here, we want to have seconds with our answer, and so that's one way to also think about it. So we're putting seconds on the top, we're putting the number of waves over here. So in 52 seconds, there are 23 waves that pass. So we're saying, well, how many seconds pass for one wave? So it's 52 divided by 23. It's going to take 2.3 seconds for one wave to travel by. Now, frequency, on the other hand, is going to be the inverse of that. We're going to be asking, well, how many waves per second? So in this case, we observe 23 waves in 52 seconds. So how many waves in 1 second? Well, we just go 23 divided by 52. We get 0.44 hertz. And if it would block the bottom there, yes. 1 divided by 0.44. So if we take our frequency answer, 1 divided by it, that's the inverse, we get our period. And so you can see how those two work hand in hand. So if you ever need to find the frequency, but you know the period, well, just take the inverse. The next example of a different type of wave, we looked at the transverse waves, is the longitudinal wave. In a longitudinal wave, the particles move in the same direction as the wave. So here, imagine that this is again a spring or a slinky, and you again pulled it and held on one end, held on the other end, and then released the one end. And so at first there was a lot of compression, and so there's going to be points of compression, and there's going to be points of rarefaction. And so we'll highlight those in just a moment. So imagine that the direction of the wave is to the right there, and the direction of the particle motion in this case is going to actually just be going back and forth, back and forth. So it's different than the transverse, which is going perpendicular to the direction of the wave. Here, it's actually moving in kind of oscillating from side to side. The point in which the spring here is compressed is called the compression point, and where it's further spread out is called the rarefaction. So this segment over here is the rarefaction, here is the compression. If you need a pause, go for it. And for a wavelength, we're measuring from the center point of one compression to the center point of the next compression. Or you could have the center point of one rarefaction faction to the center point of the next rarefaction. So make sure that it's not between compression to the rarefaction, but it's the midpoint of the compression to the next midpoint. That's going to be your wavelength when you're dealing with a longitudinal wave. So if we look at some of the definitions here, the compression is where the particles of the medium are close together. And it corresponds similarly to the transverse wave like a crest. The rarefaction, that's the area where the particles of the medium are far apart. And it corresponds to a trough on the transverse wave. Wavelength is the distance between two compressions or two rarefactions. I'll post this one later for you to take a look at. Let's deal with the last portion of this first lesson here. Formulas. Velocity of a wave can be found using the formula V is equal to lambda over t, or aka the wavelength over the period. It could also be written as velocity is equal to frequency multiplied by the wavelength. And so in these examples here, V is velocity, and for the most point, if you want to stay consistent, please try to keep it in meters per second. Wavelength is lambda, and that's usually, again, measured in meters. F is frequency, measured in hertz, or 1 over seconds. And T is period, and that's measured in seconds. So yes, sometimes they can be kind of represented kilometers an hour. My preference would be just to convert those to either meters per second. If you have a distance of kilometers, convert that to meters, just so that we're staying relatively consistent in our calculations. So we have a couple examples to take a look at, and then I'm going to get you to actually give it a try afterwards. A wave in a pool has a wavelength of 2 meters and a period of 3 seconds. Let's determine the velocity and the frequency of this wave. So often I like to think about what are my units? For velocity, units are meters per second. If we have a length over here, meters, if we have seconds over here, if I was just to intuitively think about this, meters per second, I'm going to go 2 divided by 3. But before we jump to any conclusions, let's take a look at what our formula is. And so we have a formula of velocity is equal to wavelength divided by the period. And so we have wavelength of 2, a period of 3. So indeed, we're going 2 divided by 3, and we're getting a velocity of 0.67 meters per second. And if we're going according to significant figures, we only have one sig fig, so that should be 0.7 meters per second. As for the frequency, if we already have our period and it says the period is 3 seconds, then our frequency is just 1 over 3 seconds. And so that is our actual final answer, 1/3 Hertz. And so make sure you have your units. Final example here. Red light has a wavelength of 635 nanometers. And so here you might have to grab out that book to remind yourself as to the prefix nano and what's the size of a nanometer. If the speed of light is 3 times 10 to the power of 8 meters per second, determine the frequency of the light. And the speed of light doesn't change too much depending upon the medium. Like it does change a little bit, like if you're in a different medium such as water versus air, but it's very negligible. Especially with such a large number like this. So for all intents and purposes, this is the value that we will normally use for the speed of light. Anyways, let's take a look at how do we actually go ahead and determine the frequency of light. Well, first thing is we need to recognize, well, nanometer, nano is times 10 to the negative 9. And so that's the first step there. Next, and so because you want to actually have this in meters, you don't want to have it in nanometers. You want to have your wavelength in just meters. If we want to figure out our frequency, well, here's our formula, and I didn't rearrange it, so I'm sorry. It's just velocity is equal to wavelength times frequency. If you want to, you can divide both sides by wavelength. I'm just going to plug in the values here. So my velocity is 3 times 10 to the power of 8. And it's equal to 635 times 10 to the negative 9, because we said a nanometer is to the negative 9. And then all we're going to be doing is dividing this answer on both sides of our equation to get what our frequency is. 4.7 times 10 to the power of 14 hertz. And that's our frequency. And hopefully that's informative. It gave you a little bit of understanding of the difference between a transverse wave and a longitudinal wave. There's one other quick thing here. This is another visual representation kind of what a longitudinal wave is. And so we can maybe zoom in a little bit. So you're seeing one individual particle here that's moving from left to right, back and forth again. And you can still see that the waves appear to be traveling to the right. So you can see that as the mouse cursor is going here, this looks like a wave traveling to the right like this, even though these individual particles are just moving left and right, left and right. So there's going to be points of compression, and then there's going to be points of rarefaction. So I can always include this too, just so you get a better picture. There's a variety of different types of examples here too, of different types of waves. But yeah, the ones we looked at were the transverse and the longitudinal today. That wraps it up. Now it's your turn. Good